right? So we're talking about, at this point, we're talking about differentiation. And differentiation comes just like integration comes in 3 flavors, differentiation comes in 3 flavors. And those 3 flavors are called the gradient, nabla U. Typically, we differentiate a scalar field. And then the other flavor is called the curl, which is applies to a vector field. So we differentiate a vector field and we get a vector field as a result. And then the final thing is called the divergence, which we write it as follows. So this takes in a vector field and gives me a scalar. And you can see that's suggested by the terminology. All right. Oh, one thing I wanted to do, actually, I want to record those. Thankfully, I remembered. Capturing, okay. All right, so we started talking about the gradient, and we said that the starting point for the gradient is going to be the fundamental theorem of calculus. So the fundamental theorem of calculus in one dimension states that if you integrate something from over an interval in one dimension from A to B, you have some function of x, and then you integrate that function of x dx. We can write it always as something that has to do with the boundary, right? So we write it as the difference of another function between points A and B. So you write it as fb minus fa, right? And where we find out, and this is kind of a big result in one-dimensional calculus, is that dfx over dx is small f, right? This is the fundamental theorem of calculus. And this is really, we can use this anyway to define the derivative. That's the point. So the above theorem can be used to define the derivative. So let's say on one line, on the real line, I differentiate over a small interval. I differentiate from x to x plus delta x, right? So apply the fundamental theorem of calculus, x plus delta x, and then f small x dx. We said according to the fundamental theorem of calculus, I can always write this as a function of the boundary. And that function is capital F, x plus delta x minus fx. What is the relationship between small f and capital F? We can determine that by noting that the interval, by choosing the interval of integration to be really small. If we choose the interval of integration to be really small, I can take fx out. So this becomes fx integral from x plus delta x dx equals approximately equals, right? Because we're taking the interval is not 0, it's really small. Fx plus delta x minus fx. Okay, this is equal to delta x, right? So this is just x evaluated from x plus delta x, from x to x plus delta x. There's going to be x plus delta x minus x, going to be just delta x. So this tells me that f small x, how it relates to f capital X, is as follows. It's approximately equals to fx plus delta x minus fx over delta x. This is the derivative. This is exactly the definition of the derivative. The derivative spells out naturally from this fundamental theorem of calculus, where we kind of tie the integration over a whole interval to the boundary of that interval. The first thing we encountered when trying to kind of generalize this to 3 dimensions is the concept of the gradient. And the concept of the gradient comes up naturally from line integration, specifically from line integration of conservative fields. Say I have a field that's conservative. What do I mean by a field that's conservative? Right, in one dimension, I mean, there's no concept of being conservative because there is only one way to move. You can only move from point A to point B. right? Here you can only move from point A to point B. There is no option, you can just move along this single path. In 2 dimensions, there are multiple options. So I can move like this, 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 I can move like this. If the field is conservative, it doesn't matter how I move. All that matters is the start point and the end point. So this directly suggests something like the fundamental theorem of calculus, right? Because, whatever we're doing is only dependent on the boundary. It's not dependent on what's happening. So if we have such a field, we say, hey, such a field, such a conservative field, if I integrate it from P1 to P2, f dot dl, it has to be a conservative field. It has to be for this to make sense. I can write it as just a function of the boundary. And the function of the boundary, I can write it as some function u P2 minus u P1. So this kind of makes sense. It's clear that the integration is not going to depend on anything other than the boundary. And it has a form that's similar to the fundamental theorem of calculus. And we can use this equation to derive the sort of derivative that comes out of this. So we can say that f comes out from u through some sort of derivative. So we say that f equals nabla u. Nabla is a kind of derivative. We want to understand what does this derivative mean. So we just plug it in. So this is going to be integral P1 to P2 gradient u dot dl equals u P2 minus u P1. Okay. And the trick here, this is a sum. So we have to kind of harken back to a basic property of the dot product. Dot product is linear over summation. So if I have, let's say, if I have A dot, let's say I have A dot B plus A dot C plus A dot D plus A dot E. Let's say it continues, but assume truncated after 4 terms. A is a common term, right? So from the linearity property of the dot product, I can write this as A dot B plus C plus D plus E. Right? I can distribute the dot product gets distributed over addition. Summation integration is a kind of addition, right? So I have a dot product. Now, what happens if I let P1 approach P2? If I let P1 approach P2, I get in a situation where nabla u becomes constant because the interval is so small, because now P1 and P2 are so close to each other. The distance between them, the distance between them is differential, dl. That's the line segment between them. Because they are close to each other, this becomes constant. This becomes something like this constant A. Multiplying some terms, I can take it out. So I can take delta u out and dot it with the sum, the integration of the sum, P1 to P2 dl, right? Approximately equals u P2 minus u P1. So what is this? This is essentially in 3D space, we're taking P1 and P2 to be really close to each other. Because they are really close to each other, this is between them. It's going to be just a line. It's going to be a line, and we can represent it by a vector. So this displacement vector. So this line is going to be, let's call it delta lambda. I call it lambda because lambda could be a path. So this could be a certain path, lambda, but I'm looking at really a small segment of that path. So this segment, its magnitude, delta lambda, is just the displacement, the distance, the tiny distance, right? So this is a vector, right? So I'm summing up the dl from P1 to P2. P1 and P2 are really close to each other. So this becomes a delta u dot gradient u dot delta lambda. Delta lambda is the displacement, linear displacement between 2 really close points. This approximately equals u P2 minus u P1. And now this allows us to define the derivatives. There are 2 ways to define the derivative here. Well, to understand the derivative. This is it. This totally tells us what delta U is. I can write this in two ways, and to understand this in two ways. I can write this as nabla U dot U in the direction of lambda. So this is a unity vector in the direction of our path where we're moving on the curve, right? But then I have delta lambda here, right? So this is, I can write this as you know, this vector as a unity vector in the direction of lambda times delta lambda equals UP2 minus UP1. I can take delta lambda, right? What does this look like? This looks like a derivative. In fact, this looks like a directional derivative. This looks like although the function U is three-dimensional, this looks like we kind of constrained U to a path. We're only looking at how U changes in that path, along that path. It's like a small insect flying. It's like a temperature. It's 3 dimensions. We cannot talk about function. Temperature is a function of 3 dimensions. We cannot talk about really du dt over dt, you know. But we can talk about an insect flying in the room, and as it flies, it feels different temperatures. So we can talk about that rate of change on the path. So this is the interpretation of the gradient. The gradient of a scalar field is the thing that, if it's a vector field first, is the thing at every point in space, if you dot it with a direction, you get the rate of change of that scalar field in that direction. The other way of kind of visualizing it is to take the analogy of the insect flying in 3-dimensional space. So tie it with velocity. Let's say at every point in space, we might have a velocity, right? Something flying in space along the curve. So we have the curve and we have a velocity at every point. Velocity clearly is just delta lambda over delta t. That's what velocity is, right? The displacement over change in time. So using that interpretation, I can take this and I can divide both sides by delta t. So from that point of view, I can say that nabla u dot v equals this thing divided by delta t. So it's up2 minus up1 over delta t. What happens when the 2 points get really close and delta t approaches 0? We get du over dt. Okay, so this is another way of viewing the dot product. The dot product of a scalar field is, hey, the scalar field, what happens if I traverse in space on a path at a certain velocity? At every point I'm traversing at a certain velocity, I sense a certain rate of change of the scalar field. Right? And that rate of change in the scalar field is the nabla u dot that velocity. Right? So if I have a temperature field and I'm flying through that field, at each point, depending on my velocity, I'm going to get a rate of change of temperature. That rate of change of temperature is going to depend on 2 things. It's going to depend on my velocity, how fast I'm moving, and it's going to depend on the actual gradient of the field. A scalar field is going to depend on how much the temperature field is varying in space, how fast it's varying in space. Okay, so this is the way to understand the gradient. Now the question is, so we understand what the gradient is, what sort of derivative it is. The question is now, how can we calculate it? How can we compute it, right? Because that's what we want to do. We want to, we don't want to be murky about it and you know, make a story about it in words. And ultimately, this is a computational theory. So the question is, how do we compute what the gradient is? And again, the name of the game is you have to tell me what coordinate system you're using. How you calculate it is going to depend on what your coordinate system is. So it will have, it's the same thing. The meaning behind it is the same. But the formula for it, how to calculate it, is going to depend on your coordinate system. But the result will always be the same at the end, no matter what fictional coordinate system you choose. Because the gradient is physical, real, while the coordinate system is just something that you impose on reality. There is no coordinate system in reality. It's just something we kind of like an addressing system. So let's do the gradient. Let's find out how do we calculate the gradient in Cartesian coordinates. in Cartesian coordinates. Three axes representing space. I'm flying on a path. The idea, we want to use this interpretation. So the idea is that the gradient dot the velocity is going to give me the rate of change of some function, scalar function u, scalar field u with respect to time. So let's say, yeah, but u is not a function of time. U cannot be a function direct of time. U is a function of space. So u is a function of x, y, z in the coordinate system. But however, as we're flying in space, our x and y and z are going to change. So x is going to be a function of t, y is going to be a function of t, and z is going to be a function of t. So this is how we express u as a function of t. We note that we're flying, as our flying in space, our x and y and z changes, and our x and y and z in space are going to depend on t, right? So we're moving in t changes x, y, z determines what u is. So to really find, right, in a small interval, we have a velocity vector. What is the velocity vector, by the way? What is dl? What is the linear segment? We said it's dx x hat plus dy y hat plus dz z hat. So how do you find velocity? It's dl over dt, right? So we have to divide everything by dt, dy. So the velocity is just going to be equal to dx over dt x hat plus dy over dt y hat plus dz over dt z hat. Okay, this is what the velocity is. What is du by dt? So here I want you to go back and to remember from calculus something called the chain rule. The chain rule applies if you have a function like this, a compound function, where we're trying to differentiate this with respect to t. But t, see, changing t, the thing is we want to change t's by a tiny amount and figure out how that affects u. But we don't have a direct connection between t and u. Because when we change t by a small amount, we're changing x by a small amount, y by a small amount, and z by a small amount, right? But then those three together change y. And from the linearity of the derivative, we can add those small changes together. They're additive. So the idea is that, hey, if I change t a little bit, I'm not changing u directly. I'm changing x. So there's the rate of change of x with respect to d. But then that change of x results in a change of u. How do we determine that change? We find the partial derivative of u with respect to x. Right? But that's not the only change that t causes, because t does not only change x. As t time moves on, as time sticks, t also changes y. So we have to add another, that's not the whole thing. If it was one dimension, that would be the whole story. That's what's called the compound function rule, right? Because this is a multivariable function, we have to use the chain rule. So again, the change of t causes a change in y, and that change of y then causes a change in u. So it's going to be timed by delta u, delta y, right? And then dz over dt timed by delta u, partial u over partial z. Yeah, so this is like a really basic equation from multivariable calculus. It's called the chain rule. It's similar to the product rule, only applied, and not product, sorry, the compound function rule. I forgot what it's called exactly, but it's applied to multivariable functions. And this is what I want. What does this look like? Does this look like a dot product? Remember, we established that the du by dt is going to be equal to nabla u dot v. What is the dot product of two vectors in an orthonormal basis? If I have a dot b, remember we said it's ax bx plus ay by plus az bz, right? Does this look, where is V here? This looks like a dot product, right? B is this, right? V is this, dx over dt, that's the x component of V. dy over dt, that's the y component of V. dz over dt, that's the z component of V. So we have the V vector here. What's remaining is the nabla U vector. So the form of the chain rule gives me directly a dot product. So this suggests that delta U, this directly suggests that delta U, for this to make sense, for the chain rule giving me du and dt to make sense, this suggests that nabla U has to be, grad U has to be what's remaining under the blue line, which is delta U over delta X plus delta U over delta Y plus delta U over delta Z. This is how you compute delta U in Cartesian coordinates. Okay, let's say you compute it in a different coordinate system. You'll get the same number, but it will be the same number, but you calculate it in a different way because the coordinate system is different. Sorry, I made a mistake here. This has x hat, y hat, z hat. It's a vector. The grad of U is a vector. U is a scalar. Grad U is a vector. Right. So this is how you calculate the gradient field, the gradient of a scalar field in Cartesian coordinates. Okay, simple enough. Let's say you don't have Cartesian coordinates. Let's say you have you're using another coordinate. It's convenient to use another coordinate system. How can you derive the formula for another coordinate system? We do coordinate system transformations. So we can do that exercise, let's say, for cylindrical coordinates. So the idea here is that we know that the gradient will be the same, regardless. It has physical meaning. So we have to go into the definition of the gradient and transform all of its components from one coordinate system to the other. So I'm doing it directly in the notes, but perhaps we can do it in a different way. Let's try doing it directly just to show you how the nuts and bolts works, right? And then we can do it in a different way. So we have to transform two things. First, we have, so if you want to talk about cylindrical coordinates, okay, there are two things in this equation that we have to transform. Notice this equation has Cartesian bases. We need to transform those bases themselves into the different system. We know already how to transform those matrix equations. And then we need to transform the operators. So I have delta U over delta X. I need to transform that. I need to transform that with respect to delta over delta R, and delta over delta phi, and delta over delta Z. So the idea is that we need to transform the operators. So we need to transform delta over delta X, delta over delta Y, delta over delta Z into the new coordinate system. And then we need to transform X hat, Y hat, Z hat into the new coordinate system. So the idea is simple. The idea is that how can I express that? The idea is we want to find the chain rule for those operators. So the idea is that U, essentially U, we can take it, U is a function of X, Y, Z, right? But then if you think about a different coordinate system, each X is going to be a function, let's say cylindrical, of R, phi, Z. Y is going to be a function of R, phi, Z. Z is going to be a function of R, phi, Z. So this is also a problem of multivariable calculus because U is a function of X, Y, Z, but because we have another coordinate system, we can consider X to be a function because a specific R, phi, Z is going to give me a specific X. A specific R, phi, Z is going to be specific, gives me a specific Y, and so on and so forth. So there is a function that ties one coordinate system to the other. There is a transformation. So can we always write U like this? So I can now express delta over delta X. Can I express this? Like, let's say this operator that acts on U. Can I express it in terms of the delta over delta R and delta over delta phi and delta over delta Z, right? right? We can, perhaps this is not the way to write it. Okay, I think I should write it differently. I should write, because my destination is R phi Z, so I should write R phi, which is completely equivalent, by the way, Z. But R now is a function of X, Y, Z. Phi is a function of X, Y, Z. This is completely equivalent. I just changed my perspective. Okay, so delta over with respect to delta X, right? When X changes, the way you think about this, hey, if X changes by a little bit, how does it change you? I'm giving you like that, the mental trick without memorizing the chain rule, how to write it down in any situation. If someone puts a gun to your head and says, hey, write down the chain rule, this is the way to think about it, of how to write it down. So write the function like this, and then ask yourself, delta over delta X. What happens if I change X by a small amount? When I've changed X by a small amount, I'm changing three things. I'm changing R, because when X changes, R changes a little bit, but also phi changes and Z changes a little bit, right? And then when those change, the changes, they also change U separately. And because differentiation is linear, the changes are additive. So we can take it one by one. So I change X a little bit. So that changes. So this is equivalent. So what? How does U change with respect to R? So delta over delta R. Well, X changes R a little bit. How does X change R? By a rate of delta R over delta X, right? Now also, U changes by changing phi. So if the function U, when X changes phi, right? So the function U changes with respect to the variable phi, but what is the rate of change there? It's delta phi over delta X. And then finally, when I change Z, right, that's gets multiplied by delta Z over delta X. Okay, this is the chain rule essentially. So you check that X exists here. So X is here, X is here, X is here. The rate of the change of the function with respect to X is really a sum of three different components. It's the rate of change due to X changing R. So it's going to be delta over delta R times delta R over delta X. So when X changes, it changes R a little bit. And then the rate of the function U is just how the function changes with respect to R, so on and so forth. Now the trick here, well, not the trick, I mean, the fact here is that it turns out that Z is independent of X. When it doesn't matter, Z is not a function of X. Z could, if X changes, Z would not change, right? So this is nice. This goes to 0, right? So we end up with this. This is the transformation of the operator itself. We obtain it through the chain rule. And we can continue here. And then the next step is transforming the X hat, Y hat, and Z hat. So we have to remember the coordinate transformations. We know that R equals square root X squared plus Y squared. Phi equals tan inverse Y over X. And Z equals Z. Simple enough. So I want to now apply this. I want to write D over delta X. What is delta R over delta X? It's a what do you call it? A square root, right? We know how to differentiate square root. It's a compound function. So we differentiate the square root, which is 1 over 2 square root X squared plus Y squared, and then the differentiation of what's inside the square root, which is 2X. Delta over delta R plus tan inverse. If you don't know how to differentiate tan inverse, it's 1 over tan inverse X. When you differentiate it, this is just a review from calculus, is just 1 over 1 plus X squared. Because when you integrate that, you might have studied this in calculus. Because if you, that's how it turns out. If you, I won't go through that, but you can go review calculus. But this is going to be 1 over 1 plus Y squared over X squared, and then minus Y over X squared. I'm differentiating y over x. So this is differentiation with respect to x. D over delta phi. X squared plus y squared, what is that? This is r, right? And x over r, what's x over r? Remember, x over r equals cosine phi, right? So this whole thing becomes 2 cancels with 2, and we end up with cosine phi. So I can say that delta over delta x equals cosine phi delta over delta r minus, I need to simplify this, I multiply by x squared numerator and denominator, I get minus y over x squared plus y squared. I guess I could write this as r squared. Of course, I have to repeat this same process for delta over delta y and delta over delta z. Let's do it for delta over delta y, delta over delta y. So we said when we change y, that will change r. So I put in the components. That will change phi, and that will change z. Now the question is, how does u change when I change r independently? It changes by a rate of delta r over delta y. So when I change y, it changes r, right? And at a rate of delta r over delta y, I multiply that by the rate of change of u with respect to r, right? And then delta phi over delta y, chain rule again, delta z over delta y. Again, this goes to 0. You do the same sort of thing, and you end up with delta y equals sine phi delta over delta r plus x over x squared plus y squared d over d phi. D over dz is simple. It's just d over dz. Nothing changes. And we are set. So recall that grad u is du over dx x hat plus du over dy y hat plus du over dz z hat. And we know how to transform the operator for each of those. And we know the basis vector transformation, right? I'm going to write it as a, not as a matrix equation. I'm going to write it directly. Z hat is equals z hat. That's natural. X hat is going to equal cosine phi r hat minus sine phi phi hat, and y hat is going to equal sine phi r hat plus cosine phi phi hat. And all that we need to do is plug back in. So if I plug back in, nabla u is going to be, I'm going to start with delta u over delta x. What's delta u over delta x? We already figured it out here, right? It's this, right? So this is going to be cosine phi delta u over delta r minus y over x squared plus y squared delta u over delta phi times, instead of x hat, I'm going to put in cosine phi r hat minus sine phi phi hat. And then instead of delta u over delta y, I'm going to put in this sine phi delta u over delta r plus x over x squared plus y squared delta u over delta phi times, instead of y hat, I'm going to put in sine phi r hat plus cosine phi phi hat. Finally, du over dz z hat. And all that's left is algebra, multiplying everything together. In the spirit of, doing this exercise once in your life, let's do it. Let's multiply all this algebra together, and we'll find it simplifies nicely into the form of the gradient in cylindrical coordinates. So let's see. Let me first, I want to write now everything that has to do with the r hat component, the r hat vector components. So where does that come from? So I have cosine phi r hat, and then cosine phi here. So I have cosine phi squared, sine squared phi delta u over delta r, right? And then I have this cosine phi r multiplying this. So this is going to be minus y cosine phi over x squared plus y squared du over d phi. Right? Remember, x squared plus y squared equals r squared. Right? And then, let me see. On and out, write down the phi components. There's a minus sign, so I'm going to have a minus here. So the phi components, what will I have? I have the, okay, so I have, so I took a minus, so I start with this. So it's going to be sine phi, cosine phi. So it's going to be cosine phi, sine phi. So it's going to be cosine phi, sine phi, delta u over delta r. And then there is one that's going to come from here, minus minus becomes positive. But then take the minus out, it becomes negative. So it's going to be minus y sine phi over x squared plus y squared du over d phi. So this is going to be phi. So I just essentially multiplied this into this. That's what I did. And then plus, I'm going to now multiply this into this. When I do that, I get sine squared phi du over dr plus x sine phi over x squared plus y squared du over d phi r hat. And then plus finally sine phi cosine phi, just bracket multiplication, expansion, plus x cosine phi over x squared plus y squared du over d phi, phi hat plus du over dz z hat. And then let's see what simplifications can we do. Let's see. All right, so we can simplify a bit. So this is, I can take this and I add it to this. Notice du over dr, cosine squared, sine squared. If I take du over dr out, sine squared plus cosine squared is 1. So I end up with delta u equals du over dr. And then the next, I want to take this and add it to this. So I end up with x sine phi minus y cosine phi over x squared plus y squared, right? So I end up with x sine phi minus y cosine phi over x squared plus y squared du over d phi r hat, plus now I want to take the phi hat components. So I can now take this minus plus cancels out, 0, nice. And then this is plus this. So I end up with x cosine phi plus y sine phi over x squared plus y squared du over d phi phi hat plus du over dz z hat. This should equal 0, by the way. Why is this equal 0? Well, x is r cosine phi. So this whole thing is r cosine phi sine phi. Y is r sine phi. So this is r cosine phi sine phi minus r sine phi cosine phi. 0. So this whole thing is equal 0. Okay. So nebula u is du over dr r hat. As far as the r hat component of the gradient, is the same formula as we would expect in Cartesian coordinates. However, the phi is different because what is x? X is r cosine phi. So this is r cosine squared phi. Y is r sine phi. So this is r cosine squared plus r sine squared. Take r out. R cosine squared plus sine squared is 1. So I end up with r. X squared plus y squared is r squared. So this is r squared. So this is r over r squared. So this is going to be 1 over r. So this is there is now an extra term. There is 1 over r du over d phi hat. And then there's a du over dz hat. This is how you would calculate the gradient in cylindrical coordinates. You will get the same resulting vector field as in Cartesian coordinates. The only reason the formula looks different is because the coordinate system is different. Right? So you have to know the coordinate system before you can compute the gradient. We can repeat the same exercise. I won't go through the algebra. It's just algebra. It's one of those things you have to go. It's fun. You have to go every once in your life doing it, but then it becomes something that just hey, I need to do this gradient. It's in that coordinate system. What's the transformation? What's the calculation? And you can look up a table, right? It's like integration. You don't. After a while, you practice integration a lot, but then you start just using tables. If you use tables too soon, you end up, never being able to integrate, which is not. I don't know. It's not fun. It's like you have to, on your deathbed, you have to tell yourself, at least I can integrate. So let's do that for spherical. Well, let me show you the result for spherical, and then let me show you an alternate approach to this. So I showed you the direct potatoes and meat and potatoes approach. For spherical, I go through pages of this actually, which I won't show, but it's there for reference. The same vector field. Remember, the gradient has physical meaning, but how you calculate it in spherical coordinates is as follows: du over the capital R hat plus 1 over hat du over d theta. Theta hat, this is similar to cylindrical coordinates. And then finally, the phi component is 1 over r sine theta du over d phi hat. Okay. 3 different ways of computing the gradient. 3 different ways of computing the same thing, essentially. It's the same field. The equations look different because the coordinate system is different in each situation. There's an alternate method. What's the alternate method? So let me go through this method quickly. And it should be a simpler method. So it's just by specifying velocity. So we know that u, I can write it as a function of r phi z, let's say for cylindrical. So this is for cylindrical. Right? Instead of x, y, z, r phi z. The question is, in cylindrical coordinates, what would the velocity be? So we have to remember, in cylindrical coordinates, the differential element, the segment, line segment, we know that already is going to be, I think is going to be dr r hat plus r d phi hat plus dz z hat, right? Remember? So divide that by delta t to get the velocity. So I end up with dr over dt plus r d phi over dt phi hat plus dz over dt z hat. This is what the velocity looks like in cylindrical coordinates. If you want to express the velocity of a path, of a particle on a path in cylindrical coordinates. Now the question is, remember, we established that we can tie the gradient to du over dt. What is du over dt using this understanding? Understanding that u is a function of r, phi, and z. Right? So we apply the chain rule. So this is going to be delta u over delta r, dr over dt. So we ask ourselves, how does t change r? And how does t change phi? And how does t change z? And then those 3 different coordinates are going to change u separately, and we can add these changes together. So t changes r in a certain way. We multiply it by delta u over delta r to get the total change. delta t changes phi by a certain amount. We multiply that by delta u over delta phi to get the total change. T changes z by a certain amount. We multiply that by delta u over delta z to get the total change. Okay. So again, we need to apply remember the dot product. So this is going to be, so what is delta u? Delta u is going to be the dot product. So this is delta u. This whole thing is the grad u dot the velocity. So this is a dot product. So it has two components here in each term. It has the velocity. What is the velocity here? Component. The velocity here is dr over dt is part of the velocity. dz over dt is part of the velocity. dphi over dt is not part of the velocity. We have to first, how do we can get part of the velocity? We need the r term. So I need to multiply by r here, but I don't want to change anything. I want to keep everything the same. Because I multiplied by r, I have to divide by r. This is the key thing you have to do. So this is now a component of the velocity, as we see here. So this is component of the velocity, component of the velocity, component of the velocity. What's left is the components of the other vector, according to the definition of the dot product. So this tells me directly that grad u, so we know that this thing is grad u dot v. Those red, under the red line is v. What's remaining should be the components of grad u, which should be delta u over delta r hat. Now I have this thing, 1 over r. That's when the 1 over r term comes from, having to get the velocity vector there. So it's going to be 1 over r delta u over delta phi plus phi hat plus delta u over delta z hat. And you can use this exact technique. You just have to figure out from the differential element, line segment in each coordinate system, you figure out what the velocity is. You use the understanding that the grad dot the velocity should give you du by dt. You obtain du by dt in that coordinate system using the chain rule, and then you match and you try to figure out what you kind of reverse engineer and try to figure out what the equation of the gradient is. Yeah, and you can do that for spherical coordinates, and you're going to get the same thing. That's it. We know how to calculate the gradient for all three coordinate systems. And I guess the next step now is introducing the curl. I'm not sure whether to start with the curl or the divergence. Let's see, perhaps we can start with the curl and then tackle the divergence at the end. Because the curl has to do with surface integrals. All right, we're a little bit over time. Thank you for your attention. If there are no questions, we can reconvene later. Thank you, guys. Bye.